Welcome to the state of Spack on Windows. Very similar to the last talk, except Windows, which is a lot of what I do. Just introduce myself very quickly. I'm the Windows guy. Like Greg said, I'm John Parent. I work at Kitware. I am the Spack on Windows developer, in addition to, I guess, a number of people who do bug fixes and merges, and thank you to all of that. I also do CMake, Spack tooling, and some C++ ecosystem visualizations. Happy to talk about all of that. But back on topic. Welcome to another year of Spack on Windows. Yes, we are still doing this. Just a brief roadmap, where we were, where we're gone, where we're going, and a brief revisit of why we're doing this. So back to HBSFCon 2025. I covered the brief history of the project. The first issue that actually went anywhere was 2018. That was closed in 2024 by a comment from Todd that said, CI is stable, let's close this. We covered the development background of Spack on Windows, and I declared somewhat confidently last year, we are at parity. We'll explore what that kind of meant in a little bit. But basically what that sort of meant is the core features reported, Spack, like we can do Spack things on Windows now. So the race to parity is over, more or less. What's next? Obligatory AI image. So we have parity, the basic features work. We need to stabilize Spack, right? I spent a number of hours just kind of chasing a broken develop all the time. How do we stop me from doing that? How do we build on a stable base and move forward as the project? So the first question is, how do we achieve stability? Same way you achieve stability everywhere. Testing as CI. CI was stable in 2024. Todd said it, not me. But was Spack on Windows? Not really. So yeah, how do we get there? Testing in CI. We add a ton of really robust really involved packages to CI. ParaView has dozens of dependencies. We port the unit tests that we skipped in the initial branch merge. But mostly we rely on CI. A little bit, just one more ParaView build. I added two. Sorry to the environment. But it has significantly reduced the amount of bugs in Spack develop. I spent 86% less of my time chasing bugs in a broken develop. We're running enough packages now in our GitLab CI that we're catching most of the bugs, nearly all of the bugs in the packages that we're trying to test, which means ParaView is now stably built on Windows via Spack. It also allows me to be proactive rather than reactive. I'm not chasing a completely borked ParaView stack. And it's also a stable base to build from, right? I can actually start developing features and kind of thinking long term as opposed to, oh no, everything broke the thing I fixed last week. I've got to redo what I did last week and live the same week over and over again in some kind of Groundhog Day scenario. Another way we achieve this is with integration testing. I will note this isn't actually merged yet. It's blocked on a logging rewrite. But this is a GitHub Actions-based integration test for Spack. Basically, it runs some kind of smoke test type integrations. You know, can we detect a compiler? Can we use that compiler? Is the compiler we detected functional? Can we build packages? So this has a couple really nice things. A, it allows us to kind of test more of Spack at once than the unit tests get. It also allows us to test Spack components before we waste AWS resources or UO time. It also, yeah, like I said, catches bugs beyond the scope of unit tests. That's just kind of what integration tests are for. It also catches bugs, very crucially, when there are no specs to rebuild, which is a pretty large factor of the way bugs can kind of creep into Spack without us noticing. So another thing we did this year was, now that we had a more stable base with that 86% bug reduction, which it's a bit of a hand-wavy number. I just based on how many bug fix commits I merged between the 6-month gap before I merged ParaView and the 6-month gap after. So now we have a stable base. We can start working on logging and IO redirection overhauls, which is what's blocking integration tests. So IO redirection, usually pretty straightforward with Python, right? Dupe the file descriptor, redirect it back. Not so much on Windows. Windows uses file handles, right, at the OS level, not file descriptors. Python's file descriptors on Windows are a complete abstraction. There is, in the CPython code, very, very, very deep, not part of the public API, a Windows console IO struct that holds internal references to file handles that coordinates with the Python IDs to map the kind of abstraction in the Python level. This completely breaks Spack's redirection workflow. Every time you basically dereference, basically every time Python attempts to garbage collect this struct, regardless of whether you've correctly redirected the Python level file descriptor, the file handle is deallocated behind the scenes, and the next time you go to reference it, you get an invalid file descriptor. So what we had to do is we have to now manually handle all of the file handle to file descriptor conversions and work with the Win32 API directly from Spack's Python logging API. Just a little example of that there. That is in review. It should land fairly shortly. We also spent a bunch of time working on deploying Windows binaries. So we got Spack containerized working on Windows. To the right there is an example of a Spack-based or a Spack containerized environment. So this allows us to kind of compose an environment into a Docker image. It's exactly the same thing as we have for Spack containerized for the rest of the platforms. This kind of brings us up to parity with some of the, maybe not core Spack features, but still very useful and fundamental features. Allows for really easy cloud deployment of Windows Spack environments. We also worked on a Spack deploy extension. So this is, it kind of lives in my personal GitHub repository now. I should probably move it to the Spack one. Basically, this takes a Spack environment the same way containerized does, and instead of putting it in a Docker image, it composes it into a Wix graphical installer, which is more the canonical or traditional way Windows developers are used to installing things. I'm sure we've all, download the .msi, run the .msi, stuff gets put wherever the MSI wants to put it, your registry gets entered. So basically this does all of that, but for an entire Spack environment. It's great for if you need to deploy your software to folks who are more used to the traditional Windows development workflow. It's also kind of great for release deployments. You can kind of just toss one of these up into your GitHub releases page, and it just works. It also has the added benefit of all of your runtime dependencies are available, which is a massive pain if you're on Windows, right? There's no RPaths. There's no relying on system we'll get to the RPaths. There's no relying on system libraries that are kind of just there, right? If you need to vendor your package, you have to vendor every single runtime dependency. You have to. This kind of takes care, Spack environments handle that for you inherently, and this allows you to mirror that in a traditional Windows graphical installer. We worked on Windows permissions modeling. So os.chmod on Python works, but you got to say it kind of fast. It sets the read-only bit. It can be respected, but programs also have the option to completely ignore it. So it's more of a suggestion than an actually enforced read-only bit. The actual Windows permissions model is based on access control lists populated with access control entries. So we have initial support for this in Spack with TBD. It's a better root admin check. It allows Spack to actually enforce things that we want to be read-only, or remove read-only bits that we don't want to be set. It also allows us to kind of just interact with the general system permissions model in a much more Windowsy way. This year, like I said, was a lot of bringing Spack on Windows into a more of a Windowsy approach to development as opposed to just kind of kludging Spack to work. So that's a year in things that are basically ready to ship. Coming soon in like the next 3 months, we have a number of really interesting features. We have parallelism. I have the initial job server support ready. The new installer is about 80% parity. But if we want to have parallelism, we should probably have locking working on Windows first. The issue there is Windows file locks are not atomically upgradable, so we need an entirely different locking scheme for Windows. Peter and I have been working on this for, as you can see from that PR, actually I don't know if you can see the actual commit date, but that's 2022. This PR is 4 years old almost. I've been working on this a long time, and I think we're pretty close. And once that lands, we can pretty quickly merge the job server support and the new installer support. Ideally, I'll be working on concurrently, so that will land fairly shortly after that as well. Harman did a great job of making that very easy to adapt to Windows. We're also working on compiler wrappers for Windows, and in that, RPaths for Windows. I talked a little bit about this last year. I have a little bit more to say this year because it actually works. So we have a C++-based compiler wrapper. Windows, you can't kind of execute arbitrary bash scripts without an extension, the way we do on Linux and Mac. But the C++, so I wrote a C++ executable. It does exactly the same thing as Linux and Macs for basic, compiling and linking scenarios. It just forwards all of the arguments to the compiler, the linker, and injects some Spack-based variables that you need to ensure Spack binaries get found first, or includes, etc. It's exactly one-to-one parity. But also, we add RPaths for Windows, which, if you are not familiar with Windows, that's just not a thing on the platform. If you need to link against a shared library, it either needs to be in your path environment variable or directly adjacent to the binary you're trying to run, or in a side-by-side manifest, or basically there's a whole bunch of extra steps that you have to take to make dynamic linking on Windows work without shoving all the binaries into the bin directory. So dynamic libraries are two component facets on Windows. If you're going to export symbols, there's the DLL, which is the actual shared library that you load during runtime, and there's the import library. This is the thing you actually link against. This is the .lib file that you see, CMake throwing in all your linker lines. Not to be confused with the .lib file that is a static library. They are actually both static libraries. This is just a shortened COF format version of it. Basically, it just says, these are all the symbol stubs that are available in the DLL. this is the name of the DLL. And very crucially, the import library defines the name of the DLL. And that's what Windows uses to find the DLL in the path or the bin or the side-by-side manifest. And it embeds, and when you link against a .lib, it embeds that DLL name in your, whatever's consuming it. So another DLL, an executable, et cetera, so we can find it during runtime. If you can see to the right there, that is a hex dump of a ParaView. This is actually the ParaView server binary. You might notice some absolute paths in there. I don't know if you can see my mouse, but toward the bottom here, I'll dig into that a little bit further in just a second. But I'll get to that. You run cl.exe exactly as intended. The compiler wrapper runs link exactly as intended, and then we rewrite the import library. So I run dump in on the import library, get all the symbols, remake the import library, but I overwrite the name, and I give it a mangled absolute path to the DLL. We then load the import library into memory, parse it, find the mangled name, unmangle it, and now it's an absolute path in the binary that points to some runtime artifact on Windows. And then when another DLL or an executable links to that import library, it gets the absolute path of that DLL embedded in it, along with the symbol it associates with it. And that allows you to run the binary from anywhere in your system, and it'll just find that DLL because it has the absolute path to it encoded. I know it's not a true RPath, right? RPaths involve searching and looking up a number of paths, but this is as close as without me modifying the Windows linker itself, this is probably as close as we're ever going to get. So, like I said, digging into a little bit more here, we have, again, this is the ParaView server binary, and just a random import library I grabbed from the ParaView install tree. And as you can see, there are absolute paths to my Spack install tree in both of these libraries. So if I want to take the ParaView server binary, throw it on my desktop, and just run it from there without having to create a symlink or deal with any of that, it just works. So this will allow Spack to be a little bit more dynamic. It'll also allow us to create much nicer views for Spack, and basically just makes Spack a little bit more flexible, and kind of makes development on Windows just a little bit nicer, right? I think the DLL hell is a very common complaint on Windows, right? This goes a long way in making that much, much simpler to resolve. We've also overhauled binary reuse, so I'm sure you're familiar with this screen if you've touched Windows ever, the Windows update screen. Every Windows minor build number changes every update, and this can invalidate build caches if your Windows version is older than the update number. So the solution, we need to model MSVCver and integrate into the solver. Basically, it's libc, but for Windows. The current solution is to just build all your build caches on super old Docker images, and that way you can always pull from a newer Windows version. And then, how do you use Spack on Windows? There's a Getting Started guide. There's a Windows subsection of the Getting Started guide. There's the Spack on Windows tutorial. Basically, it's the exact same Spack tutorial you've done 1,000 times, except Windows. There's the Spack on Windows Slack channel for help. Ping me on Slack. I'm also john.parent@kitware.com. And then we're thinking about doing some maybe monthly, weekly, bi-weekly Spack on Windows specific meetings to address any community concerns, help people get started. Maybe we'll do some tutorials, some buffs, something like that. And I did say at the beginning I'd talk about why we're doing this, the importance of Spack on Windows. It's necessary to support some lab codes. Corporate environments like Windows, the Department of Defense likes Windows, the gaming community loves Windows. Managing graphics stacks on Windows is an absolute nightmare. The gaming community has invested thousands, if not tens of thousands, if not hundreds of thousands of dollars into resolving this problem. And as package management goes, outside of rolling your own, Spack is like the only solution that could ever possibly handle a complex graphics and GPU-based stack for Windows. So we can target that entire industry that I think Spack doesn't really target at the moment, but it kind of just implicitly works with what the problem Spack already solves. It's also an opportunity to provide a package manager for the AI age on Windows. We can meet scientists, students, et cetera, where they are, right? Like, not every scientist or student is a Linux expert. So kind of meet them on the OSs they already have that their schools are giving out, et cetera. And we can also bring scientific development to Windows, right? Like I said, building ParaView on Windows without the CMake super build is really hard. It took me, like 3 years to get it right consistently in Spack. So now that Spack can do it every day, easily, no problem, it enables much more scientific development on Windows. And just a brief thanks to all these folks who have reviewed PRs, endured super annoying pings from me over the years, et cetera. And also, shout out to Brad King he's the original architect of that RPath. Well, I guess he came up with the idea of injecting the names into the RPath as an absolute path, into the Windows DLL as an absolute path. I just did all the C++ work, but that was Brad's brainchild. And yeah, I'll take questions.
I don't think that